Hello and welcome to Beamer. On the back of building some videos ago an arbitrary waveform generator, a link to which should be above now, and using the same principles, I thought I would explore making a 3-phase 400 Hz source. And naturally, being an AWG, the actual wave shape could be one of many, or on each phase a different shape type. Now, just to refresh ourselves, a 3-phase source represents 3 separate sine wave sources of 400 Hz, but of 120 degrees out of phase. That is, if you divide 360 by 3, that equals 120 degrees apart. The scene above is showing my old equipment demonstrating the fundamental frequency of 400 Hz, well, it's 0.4 of a kilohertz, with an error of half a hertz. With my CRT oscilloscope showing a skeleton of the sine wave waveform. And the reason why I didn't use my very sophisticated Rygo oscilloscope is the fact that the waveform and what I was working with were way too noisy. CRT based oscilloscope, old one point, modern digital oscilloscope, nil point. Let's now have a quick peruse of my breadboard for this. Firstly, on the top left we have the supply input, that's the 12.5 volts, and the power supply section with the 78L05 installed. If we travel slightly further down, we come to the 555, which is the clock of the system, and it's running precisely at 6.4 kilohertz. Now moving down to the far left, we have the reset power up circuit. Then slightly to the right of that, we have the first of 3 CD4015Bs. This is a CMOS dual 4-stage static shift register with serial input / parallel output. This is configured as a synthesized sine wave generator. Moving over to the right, the next chip, we have a quad NOR gate package that's been converted to 4 inverters. Then moving over to the third trip from the left hand side, we have phase 2 synthesized sine wave generator. Then next to it on the far right, we have the third and final sine wave generator. By the way, all CD4015s are configured to be a twisted ring type counter. Now, nestling in the top right hand corner is the LM324, configured as low pass filters and output stage. There is a spare unused op amp, which I always link the inverting input to the output and take the non-inverting input down to 0 volts. The 3 wires hanging out on the top right hand side, the bent green pin is 0 volts, and the 3 other wires are outputs. Wire green is phase 1, wire white is phase 2, and naturally blue is phase 3. Using this oscilloscope, I'm going to confirm the frequency, the fundamental frequency, and determine the phase relationships of the outputs. The time base is set to 0.5 milliseconds per division. And if we look carefully along the x-axis where the sine wave crosses here and projects forward, we have 0.5, 1, 1.5, 2 and 2.5. You have to make sure that this is exactly projecting the same image as we're looking at here. So you're looking at 2.5 milliseconds. Well, the reciprocal of that is 400 Hertz, and that confirms with our trusty counter of 400 Hertz. There are a number of ways that an oscilloscope can show the phase relationship between signals, and I've chosen this particular one. What we're looking at here is part of a wave of phase 1 output before it enters the LM324 first order filter. It offers sharp edge precision timing information, and this I can use for synchronization. The point at which I synchronize is, which is this point here, that you can't see the edge, it's a negative going edge, but it's the positive version of this point here, which is the far negative, and that's got a positive edge. Well, this up here is a negative edge, and this synchronization is sent into channel 2, and you don't actually get to see this anymore. It's just used as a reference pulse. Such are the vagaries of analog scoping. My channel 2's synchronization has shifted from the negative going edge through to the positive going edge here. So therefore my timing calculations need to change accordingly. My time base is set to 0.2 milliseconds per division. So therefore you can see that phase 2's output with reference to phase 1 is 0.2, 0.4, 0.6, 0.8 or just under milliseconds. And with opening up the time base, I was able to determine a figure of 0.776 milliseconds. I'm now noting down that figure. Finally, we're now looking at phase 3's output. Still with a time base of 0.2 milliseconds, we can start counting to the positive edge. So it's 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 1.6, 1.8. Well, it's not really 1.8. It's actually somewhere just over halfway. That would be 1.7. So we're looking at 1.7 something. And upon further analysis, I obtained a figure of 1.73 milliseconds. And I made a note of that. Before we finalise on the calculations, let's have a look at how this three-phase generator has been designed. Firstly, we have the power on reset here with C4 on power up momentarily pulling the reset line to the 4015 here. That is the reset line to phase 1, phase 1 being the master synthesizer. Moving on to the clock, the heart of the circuit, which is the 555, set to a precise frequency of 6.4 kilohertz, and it's critically adjusted by the extra resistor padding here of R1 and the additional capacitor padding of C2 here. The way I did this is that I found a resistor that brought me as close to 6.4 kilohertz as possible, but at a frequency that is slightly higher than 6.4. And then I used small ceramic capacitors from low puffage, slowly increasing the capacitance of C1 until it fell into exactly 6.4 kilohertz. The ubiquitous 555 is actually quite a good timekeeper. It's worth noting that this circuit looks complicated, but in fact is actually very simple. There's a lot of duplication involved in this. The synthesizer for phase 1 is identical to the synthesizer inside this box here for phase 2, and identical with this box here for phase 3. The only difference being is the way each block is reset, and that's why we have these green wires here, because this demonstrates the differences between the 3 blocks, which is just the way each block is reset. And I'll speak now of the internals of just one block, but bear in mind I'm actually describing all 3 blocks. The clock from the 555 goes into both A 4-bit counter and B 4-bit counter, and to make this a twisted ring counter configuration, the output of B counter has got to enter the input of A counter, and this is done via pin 2. Pin 2 is Q4B, and that goes into one inverter that inverts the signal and goes into pin 7. Pin 7 being data input of A. Other than that connection, there is the connection between the output of counter A, which is Q4A, which is pin 10, going into the input of counter B, which is the data B input, and that's on pin 15. And the resets, which is pin 6 on counter A and pin 14 on counter B, is uniquely to this block, just connected to the power up reset as I've just discussed. The only other incidental point of note is that I wasn't really fussy over the types of the materials of the resistors used in the sine wave creation network. I used whatever I had to hand, mainly 1 or 2%. I don't think the tolerance climbed up to 5%, but I used metal film, carbon film, whatever came to hand. The sine wave quality could probably be improved by having, say, 1% resistors throughout, and that was so for all 3 phases. And the resistor materials all of one sort. Now, to derive the correct phasing shift, I needed to find a way of synchronizing the other 2 phases to the first phase. Now, to do that, the only thing I could rely on is the incremental movement of the register on phase 1. And as this is not an analog control, there are only fixed increments across the 2.5 milliseconds, which is the wavelength. There are only fixed increments along that time. So the upshot of this is that I had to find an increment which, although would not sit exactly on the correct moment in time, sat as near as possible to it as I could find in the twisted ring counter. So the nearest I could find for, say, phase 2 was to reset phase 2 via this differentiator here on pin 13. That was the nearest I could find to 120 degrees. And pin 13 is Q1B output. For phase 3, via its differentiator and an inverter, it came from pin 3. And pin 3 is Q3A, and that represents the nearest timing I could achieve for the 240 degrees with reference to phase 1. I hope all of that was understandable, but I wouldn't blame you if you found that confusing, and you might have to listen to all of that again. Now, I'm pleased to say that the output is a much simpler concept. Each output is actually identical, and if we have a look at the block here, that is exactly what's in this one and that one. Firstly, we have a first order low pass filter, the gain of which is set by the ratio between these two resistors here, which is 470k over 270k. And I use the LM324. It's a very inexpensive, low quality op amp, I suppose, but it's perfectly adequate for this job, and bearing in mind the frequency is only 400 Hertz, and it operates quite well. The op amp's supply is 12 volts, and I was able to simplify the circuit slightly by referencing the positive, the non-inverting input of the op amp, each op amp, to 5 volts rather than creating a virtual half rail. Op amps don't really need to be absolutely centered around half rail. They work perfectly well referenced to a voltage that's either slightly higher or slightly lower, providing that the varying DC on the output doesn't need the absolute symmetry of a half rail. The output of 1 volt RMS is taken via the 10 microfarad here, and because that is an electrolytic, I grounded the negative side of the electrolytic via this resistor here, which I think is R17, and I just used 3 of the op amps of the quad op amp package. But for other applications and uses where you might want to change the clock frequency, say, it would be probably wise to choose a better performing op amp than this LM324. This is the 3-phase power supply circuit diagram. These components are actually mounted on the breadboard, and the supply is derived from a lead-acid battery. I tend to use a battery because it creates the quietest electrical environment. The battery supplies 12.5 volts DC, and the total current consumed by this 3-phase circuit is only 6.5 milliamps. The polyfuse protects all, and D1 is reverse protection. Should the battery polarization get reversed, this would go into full conduction and the polyfuse would open up. This is followed by a simple LED indicator, and then the 78L05, that's 100 milliamp 5 volt regulator, the output of which provides the logic with 5 volts DC, and the 12.5 volts DC is supplied to the LM324 output quad op amp, and then that's about it. Oh, and all capacitors C1, C2 and C3 are there as decoupling and stability for the 78L05. Let's now finish those calculations. I've dialed up a simple calculator online. If I now take the wavelength of 2.5 and divide it by 360, that equals that. Now commit that to memory and clear the screen. Now this is the first phase angle between phase 1 and phase 2. We noted the number, and it was 0.776, and all we have to do now is divide that by memory recall, and that will equal, well, to my reckoning, 112 degrees. As we mentioned before, not exactly spot on 120, but it is within, I suppose, 10% error. Now let's clear the screen and put in the phase number that we noted between phase 3 and phase 1. That is 1.73. Now divide that by memory recall, and that equals 249. Again, within 10%. I thought it worth mentioning that this experimental circuit is a source only. If you were to try and connect it to any rotary transformer, 3-phase, synchro servo, that sort of thing, it would need a power amplifier in between. That would be 3 power amplifiers. I am concerned about the error between the phases, and I don't know what error is acceptable, tolerable or not, or whether there shouldn't be a phase error at all. For me to eliminate phase error would complicate this circuit somewhat and represent additional components. If you know, perhaps you'll let me know in the comments below. I hope this video was of interest to you, and thank you for viewing it.